All right. So it is our pleasure to have Cheol-Hyun Cho from Seoul today, who will tell us about the Fukaya category for Landau-Ginzburg orbifolds and Berglund-Hübsch homological mirror symmetry for curved singularities. Cheol-Hyun.
Thank you very much for the invitation. I feel honored and happy to give a talk at this difficult time. We can still share ideas and communicate. So this is a joint work with Dong-Wook Chua and Won Bo-jung. Both of them were my students. They just recently graduated. And what I'm going to present is part of their thesis. And so obviously they have made big contributions. Okay, let me start. Maybe let me start by explaining the title. So by Landau-Ginzburg orbifold, I will just consider weighted homogeneous polynomials and the symmetry group, which are like a diagonal symmetry group, which means they just act on each variables, not like permuting or something, just act on each variables. So that's what I mean by Landau-Ginzburg orbifold. So if there is no group, then it's well known that you can just take the Fukaya-Seidel category of this weighted homogeneous polynomial, just slightly perturb it to have a Morse function, and then consider vanishing cycles and so on. But when you have this symmetry, somehow this perturbation and symmetry does not work well together. So it's not known how to define Fukaya category. So that's what we want to do. And so the next thing is Berglund-Hübsch homological mirror symmetry for curved singularity. What I mean is you have a polynomial, what's called invertible polynomial. And invertible means you have as many terms as variables. And if you take the exponents and it becomes a square matrix, you can take transpose and that will give another polynomial. So they are kind of dual polynomials, right? If you transpose the exponent. Also, there is some symmetry groups involved in an essential way. And if you do symplectic geometry on one side, you want to get somehow complex geometry on the other side. That's what we want to do. Okay, so is the slide working? All right, so so in the most part of the talk, we'll just talk about this x squared plus y squared with the most basic singularity. It will be still non-trivial. So what do you want to do with this x squared plus y squared? So in the symplectic geometry side, we want to think of it as a fibration. Then you have this singular fiber here, and you have this non-singular fiber, Miller fiber here, and you can do you can look at this parallel transport to singularity, which gives you this vanishing cycle, and you can define Fukaya-Seidel category of vanishing cycles. And there have been a lot of works, interesting works on Berglund-Hübsch homological mirror symmetry, starting from Seidel, Takahashi, Saito, Kaziura, Ueda, Futaki, Lakili, Ueda, Haberman, Smith, and several others, who proves that this Fukaya-Seidel category with jet grading is isomorphic to the matrix factorizations of transpose polynomial with some maximal symmetry group. Somehow, our approach is orthogonal to the approaches of previous approaches. We are going to this non-compact Lagrangian here. So we are going to use this non-compact Lagrangian, also the monodromy around this singularity, and the symmetry group in an essential way. So we want to construct some new Fukaya category out of these data. And what's the mirror? In this case, x squared plus y squared, the mirror is the same. It's again x squared plus y squared. And we want to consider matrix factorizations. So this is, you can consider one by one matrix factorization like this. It's honest factorization, or you can put them together. So x plus iy, x minus iy, and then you switch 2 and put it like this, then you get 2 by 2 matrix factorization, which if you multiply, you get this one. And up to basis change, if you change basis, then this looks like the following matrix. I mean, matrix factorization, which is yx, x minus y, and yx, x minus y. So eventually what we want to do is start from this symplectic geometry, and we count some holomorphic disks, consider some Lagrangians, count some holomorphic disks, and construct this mirror x squared plus y squared as a disk potential function. And then if you choose a Lagrangian like this, then we want to obtain this kind of matrix factorization. So that's what we want to do. Okay, so let's see how we do this. So the symmetry group is in fact quite essential. So what is the symmetry group in this case? It's G2 times G2, just acting like multiplying -1 to each variables, right? So that's the symmetry group. So we want to define this Fukaya category of this polynomial with this symmetry group and find relation to matrix factorization. Okay, so first step is we look at the Miller fiber, which is just set equal to 1, and we divide by the symmetry group, this finite group, abelian group. Okay, in G2 times G2, you have this diagonal G2 action, which is just a free action, which is just kind of half rotation. And then there is additional G2, which is you put this line and rotate with these 2 fixed points. So if you take the quotient, we get this orbifold with 2 G2 fixed point and 1 puncture. So these 2 punctures are identified. So these 2 are, so this is the orbifold. And then we consider an immersed Lagrangian in this orbifold, which kind of goes like this. And this is well known. This is called Seidel Lagrangian. And this is very important. I think it's a great insight of Paul Seidel that this Seidel Lagrangian somehow reflects the geometry of Lagrangian skeleton of this pair of pants. So if you remove these 2 orbifold points and contract, then you get the skeleton, and somehow this Lagrangian is supposed to tell you about this geometry. So we want to work on this orbifold, but it's often convenient to go upstairs and work equivariantly. So we go back to the original cylinder, and because this is 4-fold cover, so you have these 4 sectors, 4 quadrants, and each quadrant is an orbisphere. So each quadrant is divided into two triangles. So you have these two triangles inside of these triangles. Well, the big circle and small circle, these are punctures. So you think of them as points. And if you lift this immersed Lagrangian, then we get these 4 circles. So each circle projects down to Seidel Lagrangian. So these are 4 different circles. Okay, and then, so this is the, let me also explain. So for this immersed Lagrangian, we have this X, Y, Z intersections. And so this is important. We also lift these labelings in this upstairs. Okay, so now we count. We count polygons with X, Y, Z corners through a generic point. I chose a generic point. And so here is X, Y, Z triangle. Here is Y squared triangle. Here is X squared triangle. So we just add. And, sorry. So there was a question. Figure using colors. So we have this immersed Lagrangian in this orbifold, because this is obtained from this cylinder.
This I understand. This I understand. What I did not understand was your description of the next picture, where you said this circle and this circle and this circle, and you just moved very fast, and I don't know which is which, and if you can say the blue circle, the red circle, or whatever it is. It will
sorry. So they are all the same circle. They are all lifts. I just want to distinguish different lifts. It doesn't actually matter. So, so they are just, yes. So we just pick a generic point and we count. So we have these 3 polygons and there are no more. So this counting gives us this polynomial x squared plus y squared plus xyz. Okay. So this, we can say this is like a disk potential function for, it's analog of potential function for this immersed Lagrangian. Okay, now we want to get this x squared plus y squared. This is our what we want. So we set z equals 0. So this is very strange operation, but we are going to set z equals 0. Okay, so I'll explain more about this later. Then we get what we want. Now, how do we obtain matrix factorizations? We apply localized mirror functor, which I developed with Hong and Lau. How does it work? So it's somehow it's a functor from left Fukaya category to the matrix factorization of this left Fukaya category, this orbifold, or you work equivalently on upstairs. How do we do it? We just choose a Lagrangian K and we send it to matrix factorization by computing some floor complex, this floor complex. So you look at the intersection with this Seidel Lagrangian, there will be even intersections and there will be odd intersections. And we count these polygons. Usually in floor complex, you just count strips, but we allow turning corners at the Seidel Lagrangian. Seidel Lagrangian has x, y, z corners. So you're allowed to turn corners. And the claim is that this is a matrix factorization. So the idea is that the potential is defined by counting this kind of polygons. If you have any Lagrangian like this, it's going to, and this is one of your differential, this is another differential because we allow these kind of corners. And if you repeat, then that's the potential, that's the potential.
And this, Cheol-Hyun, when you do this, when you allow these corners, you allow all corners there? That is, there are self-intersections of this.
We just allow this x, y, z corners. So there are other corners, like if you have x, then there is x bar, which is the complementary corner.
Yes.
And we do not allow that.
So you make a specific choice of what
are
the jumps, branches, right?
So these angles that we choose are like the Mauro-Cartan elements, like a bounding. I mean,
right. Okay. And so basically, once you pick a Mauro-Cartan element, then in fact you can expect to have. Then you're really having a potential there. Because,
so you have a potential, and then you have this.
And in the potential, you don't count as we used to disks, but you count in fact polygons with jumps at this specific branch types.
Right. Yeah. Exactly.
Right. Great. Thank you.
So let me show you an example. So this is the non-compact. Sorry. So this is the non-compact Lagrangian that we are interested in, and I'm going to draw it here because this is the cylinder, and I draw it like this. And we have these 4 intersections. So let me label it E1, O2, O1, E2. And now let's count. So we have this polygon here. I just wrote it here. I think of it as a map from E2 to O2. Okay, so this is a map from E2 to O2. It has corner Y. So I wrote Y, I write this matrix from E2 to O2, I wrote Y here, and you actually have to compute sign, so you get minus Y. Also, you can turn additionally at Z. So you go here, come here and turn at Z. So that would be YZ. So we have a map from E2 to O1, which is YZ. So I write it here. Something like this. You have a map from this strip will count as E1 to O1 with Y. So E1 to O1 has this Y and so on. So you just count, then you get this matrix. And we also do the same from odd to even. In fact, in this particular example, we get the same matrix. And if you multiply, we get x squared plus y squared plus xyz times this.
Cheol-Hyun, sorry, I'm a bit behind. You're fast here. The different circles, as Claude asked before, you have the blue, the yellow.
Oh.
So sorry. So they are all perturbations of the same, right?
They are the lifts. They are the lifts of the Seidel Lagrangian. So
oh, right. They are the lifts of the Seidel Lagrange. No, right.
Yeah. I should have actually drawn the same color, but just to.
No, it's okay. It's all right. But because you want to count polygons, so we understand. But great. Okay, thank you very much.
Okay, and then also, so this is how we get matrix factorizations. So this is kind of very explicit. You just count polygons and you get matrix factorizations. And then we can also set z equal to 0. What happens if you set z equal to 0 is that this term yz disappears and we get the matrix that we wanted. So this is, okay. So if you set z equal to 0, then you get this yx x minus y, yx x minus y, which is the matrix that we started with, right? So this non-compact Lagrangian, we send it to this one. Okay. So in summary, what we did is we start from the Miller fiber and we divide by the symmetry group. We think of it as an orbifold, and we look at its potential function of the Seidel Lagrangian. You get this x squared plus y squared plus xyz. And if you choose any other Lagrangian k, then it will produce some matrix factorization here. And if you set z equal to 0, it will produce some matrix factorization here. And everything is a infinite functor. Did I lose everyone?
I have
this functor split is in a some end in k. Well, what is k?
So again, I think the matrix factorization you have is rank 2, but as you pointed out, there are also rank 1 matrix factorizations, which are the summands in this one you got.
Yes.
So if we believe this is meant to be an equivalence, oh, this is not an equivalence, maybe is what you're telling us.
Right, so this arrow is not an equivalence. That's a very strange arrow, yes. So this is a very strange functor, setting something to 0, which does not work very well, usually.
But which part of this diagram is Berglund-Hübsch mirror symmetry?
It's going to be something here.
Okay.
Oh, yeah, so we're going to define something here, yes. That's coming later. So let me also remark that this is the Miller fiber quotient, and this upstairs, there is an interesting result of Lekili-Ueda, which says that for any ADE of general dimension, if you look at this Miller fiber and wrapped Fukaya category, Z-graded wrapped Fukaya category, then it's equivalent to W transpose plus this, it's like XYZ. So this is some of the product of variables, but with a different grading, this maximal grading. And this is some kind of combination of C star and this finite group. So this is a different thing. Okay, and the statement, every statement here is Z2 graded version. Okay, so, okay, that's just the start. And the first theorem is that this process works for various types of polynomials, like x to the p plus y to the q, x to the p plus xy cubed, xpy, x, and the loop type, which is x to the p, xpy plus xy cubed. And so what is transpose of a polynomial let's look at the chain type. You look at x to the p plus xy to the q. Then you write exponent of each term. So this goes to p and 0. Exponent of the second term is 1 and q. And this is the matrix. You take transpose and then write the polynomial. So this is called transpose. For the Fermat type, transpose is itself. For the loop type, also transpose is itself. But for the chain type, kind of p and q is switched. Okay. And so let's see how it works for this kind of Fermat chain and loop type. So let me look at Fermat type first. So this is the Miller fiber. We divide by this maximal symmetry group. There is a G mod P action on X. There is a G mod Q action on Y. So that's the symmetry group. If the quotient is this orbifold with one puncture and this P orbifold point and Q orbifold point. For the chain type, we look at, okay, let me just do it. You look at Seidel-Lagrangian, you look at the potential function, it's similar x to the p, y to the q, plus x, y, z. And if you set z equal to 0, we get this matrix factorization. We get x to the p plus y to the q, which is what is expected. If you look at chain type, it's x to the p plus x, y, q equal 1. And the symmetry group is you multiply something to x, you multiply some lambda to x, you multiply mu to y, and it has to remain the same. So lambda to the p's power should be 1, lambda times mu to the q's power should be 1. And you can check that this is G mod PQ, some abelian group. And you take the quotient of this Miller fiber, then this again turns out to be an orbifold with 2 puncture and 1 orbifold point Q. And if you look at, if you compute the potential function, this Q orbifold point contributes to y to the Q, and you have this XYZ term, which for the small triangle. Now, the strange thing is we make this very strange restriction. We set z equal x to the p minus 1. Then this becomes the transpose polynomial. So this was the transpose, right? Somehow. To get the transpose, we make very strange restriction, okay? For the root type, the same. It's you look Miller fiber, you divide by the maximal symmetry group. Then the quotient is always pair of pants. And there is a work of Abuzaid, Aro, Efimov, Kachakov, Orlov, that this raft Fukaya category is same as matrix factorization of x, y, z. And now again, if we set, set the variable z equal x to the p minus 1 plus y to the q minus 1, then we get this transpose polynomial. Okay. So it is, okay. So the next goal is to understand this restriction. What is this restriction of z equals some polynomial of x and y? Okay, so that's the monodromy of the singularity. So let's go to the monodromy part. Okay, so we have this Miller fiber and we have singular fiber. If you go around the singular fiber, that's called monodromy. And so if I make a summary of what we did, so this is the Miller fiber quotient, wrapped Fukaya category. And we had this restriction. Now we want to somehow construct some new category here, C gamma, using this monodromy information. So that's what we want to do. And then show that this operation is mirror to the restriction. So we're consider monodromy, and this is what brings this kind of change of coordinate. I mean this kind of restriction. And the third thing we want to do is we want to prove this isomorphism downstairs. So that's what we want to do. Okay, so let's go to the monodromy. Everybody knows the monodromy of the this cylinder. I mean this Morse singularity. So the monodromy is nothing but tan twist. So you have this Lagrangian K. This is after monodromy, you get this tan twist. And there is a variation map which look at the difference of K and this phi K. So the variation map, because you consider monodromy, which by fixing the boundary, you consider this parallel transport, and the difference of K and psi phi of K is this vanishing cycle. Yeah, this is the definition of variation operator. Sorry, this has to be switched. Yeah, this is phi star minus identity. Okay. Anyway, but in this talk, I want to consider monodromy, which does not fix the boundary. So this monodromy does not fix the boundary. So what does it do? It takes this non-compact Lagrangian to the opposite side, and there is a kind of twist in the boundary, which goes like this and goes like this at the bottom, right? And the key point is that this monodromy is part of this symmetry group action. We consider this maximal symmetry group, and there was this G2 rotation, if you remember, diagonal G2 action. So this is where it goes. So this monodromy is part of this group action, and this flow at the boundary, we want to think of it as a rip flow on the contact boundary. So this is the rip flow. Okay, these two are the rip flow. Okay, then because this K to monodromy is a part of group action, if we make a quotient, what happens is this rip flow, this rip code becomes a rip orbit. So in the quotient, it becomes a rip orbit. So that's what we want to do. Okay. So we make a quotient and we get a rip orbit corresponding to monodromy, which goes around the punctual ones. So this is the quotient, and this is, I denote this as gamma. Now, we want to consider quantum cap action of this bi-monodromy orbit on wrapped Fukaya category. So by which I mean some kind of open closed map. So there is an interior insertion of this monodromy orbit, and there are the Lagrangians at the boundary. I count this kind of disks. Okay, so that's well known. But to be a quantum cap action, as Denis Oru explained in his paper, it has to lie on this some geodesic from the input to output. So we only consider the insertion of this orbit exactly at this line, right? And this is needed to make this into an action. So that you can only move like this, so that it becomes an action. And in reality, this gives an A-infinite bi-module map. So this is the module input, this is the module output, and you can imagine that disk spot popping up here and here, which is the A-infinite bi-module equation from wrapped Fukaya category to the wrapped Fukaya category. And this wrapped version, I think it's in Cheol's paper. Okay, so this is an A-infinite bi-module map of a wrapped Fukaya category, where I think of this wrapped Fukaya category as a diagonal bi-module, I mean bi-module over itself. And this cap action actually turns out to be, in our baby example, if you act the cap action by gamma orbit turns out to be equivalent to multiplication by this monodromy flow. This this is need some computation, but okay. So I want to use this monodromy flow, and so, but just describing this monodromy, I mean this monodromy by hand is not good enough. I want to have some categorical way to define it. This is how it goes. So we look at this monodromy in the quotient, it becomes an orbit, and I think of it as a cap action. Okay. So if you multiply, I mean, it's a multiplication by alpha plus beta. So if this Lagrangian has identity, if you multiply it to identity, you get alpha plus beta. So this the wrapped generators of this Lagrangian. Is it okay? I mean, just okay, that's what it is. Now, so in Lagrangian flow theory, we usually take cone over morphism, and then that corresponds to Lagrangian surgery. So if you have an element like interior intersection, then that's like doing a surgery at this corner. Even for the wrapped generator, if you have a wrapped generator, if you take a cone over this, it's like you come back like this. And so what we want to do is we want to take a cone over these two generators, alpha plus beta. That's roughly what we want to do. If you do that, then think of this Lagrangian here. You take a cone, then it goes to the next branch. And then because we take a cone here too, we get this kind of cycle, which looks like this vanishing cycle, right? So that's the intuitive idea of what we want to do. But we are not going to actually take a cone. What we are going to do is we are going to take a cone of this A infinite bimodule map. So there is an A infinite bimodule, cap action, and there is another A infinite bimodule. The cone will be another A infinite bimodule, which we call C gamma. But we are going to define a new A infinite operation here. So this will become an A infinite algebra. So the chain complex and M1 is coming from this A infinite bimodule as a cone of A infinite bimodule, but we define product, M3, M4, and so on. So it becomes an A infinite category. So this is the new A infinite category, C gamma. So the morphisms in C gamma is different from the morphisms in the category of cones.
Sorry,
so,
it's an infinity algebra, not a category, right?
It's an infinite category. So we do this for every objects. If you have Lagrangian L, L1 and L2, I'll show you what it is in the next slide. So it's a category. So not only that object, any object in wrapped Fukaya category, we can do this in all at once. And let me point
map
out
of bimodules, right? You are taking the cone of a map of bimodules.
So, right. So yes, that's what I mean. So you have A infinite bimodule homomorphism, and I take a cone. So you have something here.
Okay. And you make it into a category by adding it with the A infinite algebra of the Lagrangian or something like that, or?
It has an A infinite structure. We are going to define with new holomorphic curves.
Okay.
So we have to define it. Yeah, it's not automatic. Okay. So if you have two cones, then you can imagine that in the category of cones, you have like morphisms going directly down and morphisms going like sideways. So there are many morphisms, but the morphism will consider like only half of it. It's not not four arrows, like two of them only. And the most important thing is this. So this is a cone. So the image of cap action vanishes. And what is the image of cap action in our baby example? It's a multiplication by this alpha and beta, right? So these are wrapped generators. And if you multiply alpha and beta, it's going to kill many of the generators of wrapped Fukaya category. So most of the generators of wrapped Fukaya category will be gone. And we get a finite dimensional vector space. Okay, so that's what this construction will do. Okay, so this is, yes, so because we want something finite dimensional. I didn't mention it, so let me go back to this slide. So this is a matrix factorization of isolated singularity, and this is known to have finite dimensional Holm space. This is wrapped Fukaya category is known to have infinite dimensional Holm space. We want to create something which has finite dimensional Holm space so that it's isomorphic to this singularity side. So And this is how we kill most of the wrapped morphisms by kind of working on here. So before I actually discuss the actual construction, this is a summary, quick summary of what's going on. So if we have this singularity, variation operator is you have a Miller fiber and monodromy, and you look at monodromy homomorphism, and variation operator is looking at the difference of this variation homomorphism and identity. In our construction, we consider Miller fiber divide by the maximal symmetry group so that we get the monodromy orbit in the boundary. And the analog of monodromy homomorphism is quantum cap action. It acts on this quotient of Miller fiber to itself. And analog of variation operator is this new category C gamma, which comes by taking cones of this quantum cap action. Okay, so to define this new category, actually we have to work with the orbifold, but let me first mention the case of manifold. So we work with a manifold M and some symplectic cohomology orbit gamma. So gamma is some Reeve orbit. Then there exists a new infinite category C gamma M with the desired this distinguished triangle of infinite bimodules. So how does it construct it? On the object, it has the same objects as wrapped Fukaya category. On the morphisms, given L1 and L2, it should be something like a cone. So you look at this home of L1, L2, which is the first one. I mean, this is the middle one here. Home of L1, L2, epsilon, which is this one here, with the degree -1. And I write this element as A plus B epsilon. Okay, so the elements here is A, this is B, and this epsilon is degree -1. And we are going to define infinite operation, and we'll use what's called Popsicle structures in the domain. This is developed by Abuja, Seidel, and Seidel. You probably have heard this already. But the geometric setting is very different. But the algebraic kind of structures and the desired algebraic effects are kind of similar to the recent work of Seidel, Raptures Vibration 6. So he was, Paul Seidel also have some map, and he want to take construct an infinite structure on the cone. And anyway, so what are the popsicles? So popsicles, this kind of holomorphic disks with this kind of geodesics to specific mark points. So let's choose mark points at the boundary. So let's say I1 through IK are boundary marking. And we look at hyperbolic geodesics to these boundary markings. Okay. And right. So we have geodesics, and and the all interior mark points are only allowed on these geodesics. So these are gammas, and so at each gamma we are going to put this this gamma insertion in the interior. So that's what we will do. So you can, if we have only one line, then this is the cap action, right? You have one line, then this gamma insertion. So this is a cap action, and this is kind of general cap action, you can say, generalized cap action. Okay, and let me remark that in Abuja Seidel, this marking was not used as an input, but a place to put subclause 1 form, so that he can define, they can define this wrapped Fukaya category for using linear Hamiltonians. And in more recent work, Seidel used this continuation map. So this is place to put something for continuation map and to kill compact part, or to intersect some fiber at infinity. But somehow our use of this gamma insertion is quite different from theirs, because as I explained, the effect we want to get is this, we want to kill this monodromy. So that's what we want to do. And this is going to kill these wrapped generators of the fiber. Anyway, so how do we define some morphism using popsicles? So sorry for going back and forth. So this home space has this A part and B part. So suppose that some of the inputs are from A part, some of the inputs are from B part. Then, okay, so some of them are A, some of them are B, some of them are A, some of them are B, and so on. Then if there are B's, then we put this geodesics and put this gamma insertions. And that's the A output of the MN operation. And for the B output, we forget one of the geodesic and do not put the gamma insertion there. Then that's the B operation. And one can check from this compactification of Popsicle moduli space that this defines, so this defines A infinite category. Some definition, sorry. So for weighted homogeneous polynomials, this is how we will proceed. So for weighted homogeneous polynomials, more definitions, I'm sorry. So if you have weighted homogeneous polynomials, it means if you multiply t to the w1 through t to the wn, you get t to the h of w. So that's the definition of weighted homogeneous polynomial. Miller have shown that this monodromy is just given by multiplying this kind of root of unity to each variable. So this is the monodromy. And so from this, you can see that on the link of this singularity, in the link, we take a quotient by maximal symmetry group. So the link divided by symmetry group, there is this, they have this monodromy, and then look at the fundamental class of this link, then we get a monodromy orbit. So this part is a bit technical. We have to choose Morse function, well, very nice Morse function on this orbifold and so on, but I don't have time to discuss this. Anyway, so there is a canonical, there is a good choice of monodromy rib orbit, and we can actually work on this Miller fiber quotient. So for weighted homogeneous polynomial and for its maximal symmetry group, we take the quotient, Miller fiber quotient, denoted by X, and then we can define the monodromy rib orbit and the new infinite category. We can also define the new infinite category, even though it's orbifold. And for any subgroup, so we defined it for kind of maximal symmetry group. And for if you are having any subgroup, we can go up. So the Fukaya category of W with any subgroup is.
뭐라고? 몰라. 아닐 수도 있어.
We can take the semi-direct product. This is kind of well known that if you do it on the maximal quotient, you can go up by semi-direct product. I think it's also in Paul's work a long time ago. And so here the transpose group, sorry?
Can I ask a dumb question?
Sure.
Is this new category unitary?
I think so, yes.
Okay,
Why?
I'm just asking, is it just what you would expect, like the unit from the first component or something? Unit from
yes,
the
it has to be, most of the things come from the middle one, because you are doing cap action, most of the things come from middle one, and you're kind of killing, the cap action somehow kills other morphisms. Okay, for any finite group, you can define the transpose group. This goes back to, I think, Berglund and Henning.
Excuse me, another little interruption. So could I think, morally about this new category coming from this cone construction with as being, in fact, sort of a category associated to some immersed Lagrangians that are obtained by surgery in the way you indicated at the beginning? No.
So that was no. So yes. So the morphism space is somehow smaller. I mean, you can technically consider some category of, I mean, this cone as a twisted complex, and you can define morphisms between them and so on. Then if you have two terms, then you have like many arrows between twisted complexes. But we only have two arrows from here to here. So that's like half of the cone.
Maybe if you localize.
I also want to draw people's attention to these nice messages that Denise is sending, which we will, I don't think we will, maybe we discuss them a bit at the end. It's hard to discuss them right now because they are long, and we are only at 4/n, which means that n can be big. But we'll discuss them a moment later, maybe after the end of your talk.
Yeah, I cannot read what Denis wrote, so let me read it.
Denis says that n is 4, so this is, but still we'll discuss them later.
Yeah, n is 2 in our case. Anyway, so what I mean is, so here is the moral. So we have Miller fiber. Miller fiber is too complicated. So there is a maximal symmetry group. We go downstairs. So the Miller fibers become very simple. So for two variable case, it becomes just pair of pants with some orbifold compactification. Then you can do some mirror construction. So in higher dimension also, I think Nick is here, but in higher dimension, you can expect that it becomes, if you have invertible polynomial, and if you look at Miller fiber, then it should go down to this higher dimensional pair of pants with some orbifold compactification. And maybe Nick's immersed sphere should play this fundamental role there. So we go to the maximal quotient, and if you want to go up, the way to go up is rather well known. It's like taking some semi-direct product. So let me not mention it. So we just do it on the maximal quotient, and then you can obtain something above by algebraic method. Okay, so what this means for our curve singularity. So what is the monodromy for curve singularity? So these curve singularities, I mean, Fermat chain loop, they are all weighted homogeneous polynomials. So they have this monodromy orbit, right? And also we quotient by maximal symmetry group. And so in each case, we have this, monodromy orbit. In Fermat case, monodromy orbit turns out to be this going just around this puncture once. So this is gamma 3. For the chain type, it rotates gamma 1 p minus 1 times, and it rotates gamma 3 once. And for the loop type, it rotates gamma 3 once, gamma 1 p minus 1 times, gamma 2 p minus q minus 1 times. So, and then from this monodromy orbit, we can define some polynomial using the idea of Kodaira-Spencer map or closed open map or something. So it's just this map. We have this monodromy orbit and count disks with this insertion and with boundary corners. Then in Amorim and in the work of Amorim and Hong and Lau, we did this for immersed Seidel Lagrangian, and for Fukaya Ota Ono defined it for toric manifolds. Anyway, the important thing is the output is, anyway, so we have to generalize this for this symplectic cohomology class, but anyway, output is a multiple of unit. And if you take the coefficient, like the corners, labeling corners, then this gamma will get only z. So you see there is this disk with a z corner, so that gives us z. And this, for the chain type, we have z minus x to the p minus 1. So this z comes from gamma 3, and x to the p minus 1 comes from this, this disk, which rotates kind of p minus 1 times. And the same for the loop type. So this mysterious restriction that we had is nothing but the monodromy of the punctures of the Miller-Fiber quotient. So that's our interpretation. Okay, so let's go to the main statement. So let's go to the invertible curve singularity. This means variable, we only have two variables. Then the first statement is the cap action of the monodromy orbit is mirror to the hypersurface restriction. This is not difficult. So previously I explained what is this quantum cap action. And I also explained what is this localized mirror functor, which is you look at corners on one side of your strip. So this is the corners. And we just combine those two. Then there is a homotopy moving this gamma W to the boundary with B's. Then you'll have this bubble with this gamma W insertion in the interior. And we just saw that this is the Kodaira-Spencer map. So this is Kodaira-Spencer map, some element of Jacobian ring times identity. So this M2 becomes trivial. So this becomes just multiplication. So this is the multiplication by Kodaira-Spencer image. So this homotopy describes this commutative diagram up to homotopy. So this cap action is this multiplication by this guy. And so this is kind of some kind of DG model for this matrix factorization where you set this equals 0. So this, if you restrict this to be 0, then you get transpose. We saw that this gives us transpose mirror. And so from this diagram, we obtain this Berglund-Hübsch homological mirror symmetry. So this is defined also using some configurations like this. Okay. All right, and if Berglund-Hübsch for general form, for any subgroup, you can go up by taking some semi-direct products. So it's some Fukaya category of M and some subgroup G should be mirrored to matrix factorization, G transpose matrix factorization of W transpose. And this, both of them as G2 graded categories. Okay, so let me move on to slightly different direction. So we apply this to ADE curve singularity W transpose. So we work in the case when W transpose is ADE singularity. Okay, so you take ADE singularity and actually take transpose and look at Miller fiber and divide by this symmetry group. And we can find all Lagrangians corresponding to indecomposable matrix factorizations of this W transpose. That's the theorem. And we realize Oslander right-hand exact sequence as Lagrangian surgeries. So I'll explain what this means in this E7 example. So let's go to E7. Okay, so this is the E7 Miller fiber, which is x cubed plus xy cubed equal 1. This is a genus 3 surface, and this we described where to glue. This A is glued to here, B is glued here, and so on. This you can glue, you get a genus 3 surface. And because the transpose is y cubed plus yx cubed, so it looks similar, right? It's kind of self dual. And let's look at matrix factorization side. It's kind of, there is an interesting story. So for E7 singularity, x cubed plus xy cubed, in the 90s, the algebraists worked out the theory of maximal Cohen-Macaulay modules over Cohen-Macaulay rings. This means just matrix factorizations, G2 graded matrix factorizations. And they found all indecomposable matrix factorizations. So this is the list. So you A, B, M, Y, C, D, Y, and so on. So what are those? A is this 1x1 matrix factorization. C, D, this 2x2 matrix factorization. M, N, given by M1, M2, and these are given by these. So there is one collection and there is another collection. So connected by this dot, they are obtained by just switching two matrices. That's the Oslander transpose. X, so this X and Y, they are 3x3 and so on. Okay, and oh, sorry, x3, x1, x2 are 3 by 3, x3 and y3 are 4 by 4. And we want to, so the claim is that we can find all this matrix factorization using Lagrangians in this Miller fiber. So let me show you the answer. So this is the answer. So kind of, there's A, if you reverse the orientation, that's B. So there is M2, Y, D, and M1 and Y3 and so on. So let's see how Y3, I mean, how this works. So you go to this Miller fiber. Okay, so this dotted line, this is the lift of Seidel Lagrangian. So this is the lift of Seidel Lagrangian. Okay, so you see that in the intersections of this dotted line, you have these X, Y, Z variables. Okay, this is what we are going to read. And if you have this any non-compact curve, then we count. So this will contribute to Y from this intersection to that intersection. And this has Y corner, it's another Y. This is Z, and you have this Y squared, and this is X, and so on. So by counting, and there are many others, by counting, you can actually recover this X3 and Y3. So that's what it is. But in fact, so this epsilon, I mean, so this X3, Y3 is some kind of cone of this gamma and delta with this morphism, Y squared, Y squared. But in fact, in Yoshino's book, it's written as Y00Y. And we think it's a typo, but it took like 1 year for us to figure this out. Anyway, so what do I mean by AR's exact sequence? So these indecomposable matrix factorizations are kind of related by very special exact sequences. And the first one is A, so 0 goes to A, goes to M2 and B. So let me show you how to read this from this AR quiver. So there is A. You start from A and look at all the arrows going out from A. So you have M2. And then you look at all the arrows going to the dotted partner of A, so B, which is B. So you start from A, go to M2, and come back to B. So that's the exact sequence. If you start with M2, then from M2, you can go either B or Y2. So from M2, you go to B direction Y2, and then you can come back to N2. So that's another exact sequence. You see this M2, B direction Y2, and N2. So that's the exact sequence. Okay, and we want to realize it as Lagrangian surgery, all these as Lagrangian surgeries. So let me show you how this works. So this is the full list. Let's go by one. We'll just go 2 of them. All right, so A is actually this, the shortest line. A is the 1-by-1 matrix factorization, the simplest one. This, we go from this square to this circle. This is A. And if you multiply group action, this maps to from this square to this one also. And so if you reverse the direction, it becomes B. And we look at this morphism, and when we make a cone, so we make a surgery, then this is M2. So this is the first exact sequence. And the second exact sequence is more strange. So this is N2, and orientation reversal is M2. But we need to work with a kind of different geometric model. So so orientation reversal, this is M2, but we also claim that this is also M2. And so with this orientation, this is M2, this is N2. And if you take surgery here, then you get B and Y2. That's the desired exact sequence. Okay, so I said these are equivalence of categories, right? One side, it's a geometry of the Miller fiber. The other side, the matrix factorization. How could different Lagrangians map to the same matrix factorization and still could be an equivalence? So this because this is because we are working not on the rep category, but we take a quotient by cap action. So morally, these two are related by cap action. And another way to see it is this N2 I explained is obtained by a surgery of A and B, right? This is, if you do the surgery, you get M2. But I also said you have two, I mean, the monodromy is like a sum of two orbits. So you have one orbit and the other orbit. And so surgery, taking a surgery in one orbit is equivalent to, I mean, because we are taking a cone of, sorry, cone of something like alpha plus beta. So this kind of makes cone of alpha is equal to cone over beta. So this is alpha, and I mean, this is alpha and this is beta. So that's why this Lagrangian is identified with this Lagrangian in the quotient. So somehow everything works out well, and it looks like it's not an equivalence. Two different Lagrangians go to the same Lagrange, same matrix factorization, but in fact, when you go to this new category C gamma, they are actually the isomorphic objects. So there is no contradiction. And so the reason we struggled is we wanted to find this geometric model for AR sequences, and there are so many morphisms, so we don't know which one to take cone, which one to take surgery. So it took, and then somehow the version with y00y corresponds to this Lagrangian, and the one with which we worked, it corresponds to this Lagrangian, and somehow, anyway, so that's the story. So this, we can do this for all ADE singularities, and these are the all indecomposables. One more comment is that if you look at this, if you start from A, and B is like shift by one. So from A, and using this cone, you can construct M2. So what this means is that any element in AR sequence turns out to be a split generator. Any element is a split generator. So knowing a split generator and knowing all indecomposable matrix factorization is kind of different information. So if you just know one, then it's a split generator. So you can generate category, but knowing precise indecomposable matrix factorization requires more effort. Anyway, that's what I wanted to say. Thank you.
Okay, thank you very much. Thanks for this talk. Let's see if there are any questions. So we'll discuss Denis's comments, but let's see first if there are any other questions directly to.
Hey, I have a question. Cheol-Hyun, is there some homological definition of the gamma that you are using?
Yes. So we are looking at Miller fiber quotient, right? So the boundary is a link, and the link will be also get quotiented, and we are kind of taking the fundamental class, orbit corresponding to the fundamental class of this link quotient. Does that? I mean, you look at local flow homology and take the one for fundamental class.
Okay, thank you. And maybe a follow-up question. So you think of this gamma as a class in a certain homology?
Yes, yes, symplectic homology, yes.
Symplectic homology. So what properties, what abstract properties of this gamma are you using to define the category C gamma?
So in one of the theorem we have, I mean, so you can define the C gamma, category C gamma with any gamma. So any symplectic homology class, you can define it. So, and this is just the popsicles and so on. So there is no restriction, but so which category we want to use, we just use the one given by this monodromy of the singularity. Does that answer your question?
Yes, thank you very much.
All right, so let's see, maybe if there are any other questions. So we can come back to them also later. So Denis, why don't you tell us a little bit what is in your messages? So we might have read them, but.
Sure, I'll be very quick because I'm teaching in less than 10 minutes. So just I wanted only to point out that the construction, the main construction might look mysterious at the outset. And it's an instance of a general phenomenon that very often, if you have a fibration and you know that the smooth fiber of it is mirrored to something on the algebraic side, then the total space of the fibration ends up being mirrored to a hypersurface in that thing. So this is something that also shows up in my work with Abu Zaid on mirror symmetry for hypersurfaces. But of course, the example here is different. And so the general language that helps you see this, and if you go back through the relevant slides of the talk in this way, it's completely apparent, is that whenever you have a fibration, say with just one singular fiber for simplicity, there's a natural transformation from identity to the monodromy, acting on the, looking at the Fukaya category of the fiber. There's a natural transformation from identity to the monodromy, which counts sections of the fibration over a U-shaped region with boundary on the parallel transport of a fiber Lagrangian. So this monodromy here, the monodromy here happens to be trivial. And so the natural transformation goes from identity to itself, which means it's a class in the Hochschild cohomology of the category of the fiber, which is isomorphic to the symplectic cohomology, hence the reinterpretation. Now, this doesn't tell you how to calculate it. The calculation part is the interesting geometric meat of these kinds of arguments. And that was the meat of the talk. But once you have that general structure, then it's a general argument that the Fukaya category of a total space is the limit of a diagram involving two copies of a category of a fiber and this natural transformation as connecting map. And algebraically, this is equivalent to using, fancy word would be causal complexes or something. Anyway, to do algebraic geometry on a hypersurface, you can do algebraic geometry on the ambient space and then take the co-kernel of a map given by multiplication by the defining equation. And so this is what comes out of these calculations. So I just wanted to point out that this talk is a beautiful example of this phenomenon. And I was hoping that this might clarify in the minds of some people why this works and what is going on here.
All right, so thank you very much, Denis. So good luck with your teaching if you have to run off. Any other comments and or questions or remarks? I'm trying to look around here. No other questions. So, okay, let's thank Cheol-Hyun again for a very nice talk and interesting, difficult subject, actually. So please don't forget to send me your slides, Cheol-Hyun. So I'll post them soon. And, okay. I think, well, we're kind of done with the sort of formal part of the meeting. We can, if there are any other comments or questions, we can still discuss them. A funny comment, or not funny, I don't know. So Dan has a beard again. So this is
That's right, yeah.
just noticed. But,
actually, I'd like to shave it. I just have been so busy changing diapers that I haven't. So enjoy it while you can,
right,
I guess.
yeah.
I'll
So,
shave.
in any case, it's I remembered your beard, but like different colors before. Now it's very, it has a very nice, interesting shade.
Yeah. Yeah, I mean, you know, when I was younger, it was like totally black, which I liked better. Now it's sort of
Right. Well,
mostly gray with some black.
Yeah, I think you had to work to get it to be a bit white, so you should be proud of it.
That's right. That's right. Yeah. With each lemma I have to get correct, it turns a little
Right. Exactly. I sympathize a lot.
Right.
Okay. Well, all right. So, Nick, nice seeing you. I haven't seen you in a while. It's great seeing you here. So I think you also are experienced with diapers and stuff, maybe.
Yeah.
Also. All right. So, okay. So, yeah, I always try to see and. All right. Well, I mean, it's we're ending tiny little bit earlier than usual, but that's fine. I mean, it was a nice talk, and it was very nice seeing you all.
Yeah, it's good to see everybody. I mean,
I
haven't seen you in a while either, Nick. So
yeah.
good to see you.
Hey. Yeah.
Hi.
So I'm gonna stick around a little bit, but okay, like the you know, you can run away if you want to.
Things are good in Montreal?
Well, good is, you know, they are good going to bed. So
good is always a relative concept.
Yeah, I mean, they are in fact very good in a way, in the sense that right now, you know, it's a beautiful fall and, you know, schools are open. We're teaching online, which in fact, I think it's fine. We got used to it. I think I don't feel it difficult. But okay, the question is basically for when things will close and how much. And
but so far it's stable?
No, it's not stable. So that's the thing. So it's exponentially growing.
I see.
But the numbers are still small. But the thing is, you know, I think Leonid mentioned this before, that it's an opportunity to learn again what an exponential means.
Right, right.
And so numbers are low now, but in 5 weeks, 6 weeks, the question will be, we're closing what and for how long? So this is obvious.
I kind of feel like things didn't actually get better. It's just people got bored of all the precautions and now they're ignoring
right.
it.
So the threshold for closing, it's much higher now. But nonetheless, if you wait for things to get to the threshold, it will be reached. So this is true, I think, everywhere. It's a higher threshold for pain because people kind of got used to this and feel like, okay, it's bad, but it's not too bad, up to a point, which is basically decided by the moment hospitals get filled up. So then.
So have the leaves turned over in Montreal yet?
Yes, very much so, yes. Here we're kind of almost half Indian summer already, but we still have like the most beautiful period is coming, but yeah.
It's just starting here in Massachusetts.
Yeah, of course. And in Princeton, it's still green, I guess.
Yeah, I'm actually in Rhode Island myself, but
right. But
so we're pretty similar to Massachusetts. It makes me a little sad. Normally, I'm excited for the onset of winter, but it feels like Game of Thrones or something, where winter is coming and it's not going to be very nice or whatever.
It's actually turning colorful here as well, I think. Which I noticed just now, so it's strange, but.
I got myself a heat lamp for my patio before they all get completely sold out.
That's smart.
Yeah, actually, I remember when I spent a year in Princeton, I realized that heating there is sometimes iffy. So it's better to have some additional support.
So you stayed in institute or you stayed somewhere else?
Sorry?
Where did you stay?
Well, I stayed on at IAS, so I stayed in some residence there, and at some moment they had some heating issues, so I
really?
had to run very well fast and get you know, an electric heater or something. It was a problem just for a few days. It wasn't a big deal, but yeah. In any case, I look forward going back there once at some point.
There was this Hurricane Sandy that knocked out people's power, and the institute was sort of like 10 days without heating in their buildings, and or refrigerators and things like this. So they tried leaving. Some people tried leaving food outside, but beers were too interested in it.
Right. That sounds yeah. Well, if you don't have electricity now, you're really out of business, because no teaching, nothing. It's like total.
You can go to your office, I guess.
Right. So you see, for us, it's going to the office is allowed, but not recommended at all. So I've not been to my office.
Anyway, so, but if you are stuck without electricity, I think they would just make an exception.
I don't know. Maybe. In any case, let's hope we don't lose it, and that Princeton doesn't either. In Montreal, you can only basically lose electricity for two reasons: an earthquake. We didn't have big ones, very small ones, but it could be, or ice storm. So this have happened a few times. So those are very bad for some parts of the city.
Ice storms sounds bad.
Yes, ice storm. So, you know, like you have this big, thick kind of covers of ice on all electrical cables, and where electrical cables are outside, they also on trees, and the trees break, and also they fall on electric cables, and that's it.
Right, that's regular storm damage.
Yeah, but I mean, these ice storms are like, you know, you see maybe like a cover of maybe a centimeter or 2 centimeters thick ice, so that's very destructive. And there was one like this, I don't know, people still remember it who lived here. I wasn't here, but when they lost electricity for maybe 10 days or something. It was like in the middle of winter. So here it's really cold, you know, so it's a big issue. In any case, let's hope this doesn't quite happen so soon. And all right, so guys, everyone, well, let's meet again next week. And thank you very much for the talk. I don't know if, I think you're still here. Thanks a lot. Thanks for staying awake so late for you. And well, hopefully you'll stay also awake for other talks. Can come. And see you all next week.